So, hello everyone again. This is lecture 1 part 3 of current electricity. In the previous lecture we started with the discussions on electric current in conductors, in which we first devised if what happens when there is no electric field and what happens in when there is an electric field. The complete discussions of what is happening when there is an electric field is not being done. Today we will complete that discussion and after that we will move on to Ohm's law. So, in the previous discussion what we understood is that if there is no electric field present, then there is no charge, hence no complete charge movement from point A to point B, because the amount of charges moving from point A to point B is equal to amount of charges moving from point B to point A. Hence delta Q is 0, and because delta Q is 0, the amount of I which is 0. Now, what will happen in another case in which electric field is present? In the previous lecture I explained you the complete model of the dielectric disc being kept like this, and the movement was being done in this direction because the electric field is present, but the electrons will flow in opposite direction. So, I am Sameer Lavankar. Let us begin our discussion regarding this topic. So, first of all, let me explain to you the course outline. So, in the first point the introduction was being done, in which I tried to explain to you what is the difference between the charges being kept at rest and what happens when there is a movement of charge from point A to point B. Next, in the another concept of electric current, we defined what is electric current. I explained you two different formulas. One was due to the I, which is equal to Q by T, and another was the limit formula, in which we generalize the concept of electric current, and we devise that I is equal to delta T limit delta T tending to 0 delta Q by delta T, where delta Q is the amount of charges moving from point A to point B through a conductor. Right now we are in third point, that is electric current in conductors. In this electric current in conductors, the first concept of current being produced if there is no electric field is being told about, that is there is no electric current being produced. Now, let us go on to further discussions of this part only, in which we will try to find out if there is an electric field present, will there be electric current produced or not. So, let us just directly go into this concept only. So, electric current in conductors. So, this thing is being explained to you. So, here, so this was the complete disc. So, I think I explained you this portion, this portion, this portion, this portion is also being explained, and then electric field was being created also. Okay. So, now they will thus move to neutralize the charges. So, what will try to utilize the charges? These electrons, these electron particles which are moving from point A, from this point to this point, will lead to this portion. And as we know that the plus and minus will cancel each other, hence it will try to neutralize the charges at this electric disc. So, the electrons, as long as they are moving, will constitute an electric current, quite evident, because as long as these are moving, so they will. So, please now look at the physics of this. So, what was happening is there was a dielectric charge, there was an electric disc being kept here, there was an electric disc being kept here. Let us say the amount of charges be 10 here and 10 here. When the electric field is being obtained, then these negative charges will try to move in this direction. We know that there is a movement, we are just assuming this to be conductors, such type of conductors in which the electric current is produced only and only due to the movement of negatively charged particles called as electrons. Now, if we are only assuming that the negatively charged particle movement of negatively charged particles constitutes a current, therefore, in this direction, in this way, we are assuming that these negative charges are moving. If these negative electrons are being moving, hence then electric current is produced. But these electric current will only be produced till we are assuming that there are 10 charges here, 10 charges here. These 10 charges will move from this point to this point. At the time when these 10 charges are being neutralized, there is no electric field produced, and in the previous case we already studied that if there is no electric field, there is no electric current. Hence, we derived or devised a new concept in which we understood that the electric current will only be produced till there is no complete neutralization of charges. Whose charges? Positive charges, or let us suppose the complete charges of plus and minus in this case. Okay. So, this thing is being dealt with here, that the electrons, as long as they are moving, will constitute an electric current. Hence, in the situation considered, there will be a current for a very short time while, quite evident that there will be only and only current produced in this conductor till the amount is being not neutralized. and no current thereafter. Quite evident, because in the because after the charges are being neutralized, there is again no electric field, and we understood in the previous case only that if there is no electric field, there is no electric current. Okay. Next, we can also imagine a mechanism where the ends of the cylinders are supplied with fresh charges to make up for any charges neutralized by electrons moving inside the conductor. So, what does it try to say is, let us suppose these dielectric discs are attached to a mechanism. So, let us say this be that mechanism, which are supplying positive charges here and negative charges here. So, if this mechanism supplies constantly all the positive charges towards the left direction and negative charges towards the right direction, there will be always an electric field in this place, and if there is an electric field present, then the electrons will move from negative to positive direction, and if the negative if there is a movement of negatively charged electrons from, let us say, point B to point A, then there will be electric current. Hence, if this as long as this mechanism is taking place, we can be sure that there is an electric current being produced. So, let me just iterate this line again, that we can also imagine a mechanism where the ends of the cylinder are supplied with fresh charges to make up for any charges neutralized by electrons moving inside the conductor. Quite evident. In that case, there will be a steady electric field in the body of the conductor as long as this mechanism is being working. So, the electric current will be produced. This will result in a continuous current rather than a current for a short period of time. So, if this mechanism is not being involved, then the current will be produced only for a short period of time, but if there is a mechanism, if there is a continuous mechanism, then the continuous current can be visible, or continuous current can be felt or devised. So, mechanisms which maintain a steady electric field are cells or batteries that we shall study later in this chapter. So, these mechanisms are nothing but cells or batteries. So, what the cells and batteries try to do is, they try to maintain a constant potential difference across the conductor, and due to that we get constant steady electric current. So, finally, this is the end of your electric current in conductors. In this the concept which we understood is, first of all we understood this concept that if there is no electric field applied, then there will be no electric current. If there is electric field applied, then there are divided into two cases. First of all, we are only assuming an electric field such that we are taking a disc of dielectric in left direction and right direction, and due to that we are assuming an electric current being produced. Why is the electric current produced? Electric current is produced because there is a movement of electrons from, let us say, B point to A point. This is only valid till the complete neutralization has not happened. If we devise a mechanism such that the neutralization is never able to be achieved, that is, we try to supply the positive charges in left direction and negative charges in right direction, then there will be always electric field surrounding the current, and due to that electric field there will be negatively charged particles always moving from this point to this point, and because the movement of charges constitute an electric current, hence it can be said finally that an electric field, if there is an electric field present, if there is a steady electric field present with a mechanism such as a cell or a battery, then there will be a electric current being produced. So, this is the complete concept of electric current in conductors. Now, let us move on to another concept, a very beautiful law which is very important for complete understanding of current electricity, which is Ohm's law. You may have heard this in your previous classes also, what is an Ohm's law. So, let us devise it again and let us use it in our subsequent slides. So, next is your Ohm's law. So, a basic law regarding the flow of current was discovered by G.S. Ohm, a very prominent scientist, in 1828, long before the physical mechanism responsible for the flow of current was discovered. So, as you can see, before even it was derived, what is current, how it is, how the passage of current is being dealt with. He discovered this concept of Ohm's law even before that. So, the current concept came into picture after many years, even before that Ohm's law was derived. So, you can see that there was a reverse engineering being done even in the concepts of physics here. Okay. So, a basic law regarding the flow of current was discovered by G. S. Ohm in 1828, long before the physical mechanism responsible for the flow of current was discovered. Now, what was the complete theory? Please look over here quite carefully. So, imagine a conductor through which a current I is flowing, and let V be the potential difference between the ends of the conductor. So, what we are assuming is, let us suppose I draw a conductor here. So, here imagine a conductor through which a current I is flowing. So, let us suppose that this is the conductor I was explaining you. Let us say this cylinder is the conductor and through which a current I is being flowing. So, this, let us say this is the direction of flow of current, and let V be the potential difference between the ends of the conductor. So, one of the mechanism through which we can maintain a potential difference between the left hand and the right hand is a battery. So, I just made a battery here, and due to that a potential difference was being observed between the left hand and the right hand. Now, the Ohm's law states that, Ohm's law states what? Ohm's law states that it was being defined that the amount of potential difference was always proportional to the current passing through the conductor. That is, we assumed that V is proportional to I. If we need to remove this proportionality sign, we can just write it as a factor K into I. This factor K by the prominent scientist Ohm's was called as R. Hence, we found a formula which is equal to V is equal to R I, where R is called as resistance of the conductor. Where R is called as the resistance of the conductor. So, just let me iterate it again. So, what is written here? Then Ohm's law states that V is proportional to I or V is equal to Ri, where the constant of proportionality R is called as the resistance of the conductor, where the proportionality R is called as the resistance of the conductor. The SI units of resistance is ohms. So, you just need to remember this, the SI unit is ohms, for the SI unit of current is amperes, I R, and the denotation is by A. The denotation here is like this. So, the denotation is by symbol ohms. Okay. So, this thing is also being explained, this thing is also being explained. Next, the resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. So, how it is being depending on the material of the conductor and also dimension of conductor will be dealt in subsequent slides, but for now you just need to remember that it not only depends on the material of the conductor, it also depends on the what we can say dimensions of the conductor, such as length, etc., length, area, etc. Okay. So, this is the initial statements of Ohm's law. Let us move on to further discussions. So, what does it try to say is what now we did some experiments which is based on dividing the length of the conductor into two parts or dividing the area into two parts and trying to devise. So, this is completely the concept of the series of resistors and parallel resistors. So, just please look into this. I will try to explain to you again if you cannot understand this. So, dependence of R on the dimensions of the conductor can easily be determined as follows. So, as in the last point we tried to understand the concept of R as how it is depending on the dimensions of the conductor. So, that complete explanation is being explained here. So, dependence of R on the dimensions of the conductor can easily be determined as follows. First, consider a conductor satisfying above equation to be in the form of a slab of length L and cross sectional area A. So, as you can see here, so I am explaining this to be a conductor here which has a resistance R, and this is the area A. So, this is the cross section area A, and this is the length L. So, everything is being written here directly. I do not need to mark everything here. I am just explaining this to be a conductor with the resistance R. Okay. So, consider a conductor satisfying the above equation to be in the form of a slab of length L and cross section area A. Next, imagine placing two such identical slabs side by side. So, now what I try to do is I just try to place two such identical conductors like this, which is a resistance R, such that now the complete total length will be equal to 2L and the area, as you can see, is A only. The area is cross section area is A only. So, imagine placing two such identical slabs side by side, so that the length of the combination is 2L. Quite evident, as you can see, the length of the combination is 2L here. Okay. The current flowing through the combination is the same as that flowing through either of the slabs. Quite evident, the current flowing through this will be I only, and the current flowing through complete will be again I only. Next, if V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab, since the second slab is identical to the first and the same current I flows through both. So, what does it try to say is, if the potential difference across these portions, let us say I write VA and VB to the potential. So, the potential difference, that is VA minus VB, was coming to be V, then it was being devised that the, let us say I take 3 cases here, let us say write VA, VB, VC, then here also VA minus VB is V and VB minus VC is also V. That means the potential difference across the conductor is always V. Okay. Next, if V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab, since the second slab is identical to the first and the same current I flows through both. So, because we are assuming the concept that the dimensions are same, we are assuming that if the current I is passing through it and it is having a potential difference of V, therefore, in this combination also for the first slab the potential difference will be V, and for the second slab also the potential difference will be V. The potential difference across the ends of the combination is clearly a sum of the potential difference across the two individual slabs and hence equals to V. So, hence as the potential difference across this is V, as the potential difference across this is V, hence the complete potential difference will be 2V. Therefore, the current through the combination is I and the resistance of the combination is denoted by RC is nothing but total potential difference is 2V. Therefore, the complete combination which we will get is RC is equal to 2R. So, this is a complete simple example of series of resistors only. This is complete concept being devised, how the series of resistors, how the combination of resistors is being explained upon. Therefore, let me end the class with this concept only. So, finally, what we got is for the combination of two resistors or two conductors being kept side by side with the same identical dimensions of L and cross section area A, the combination resistance which we will get is equal to 2R, that is R plus R, since V by I is R and the resistance of which is the resistance of the either of the slabs. So, let me stop it here only. In this lecture I just explained you the electric current in conductors. So, the electric current is produced as long as the electric field is applied and it is not produced when the electric field is not present. Then we devise the Ohm's law, that is V is proportional to I, V is equal to Ri, where R is the proportionality constant which is called as resistance and is denoted by ohms. And finally, I explained you the concept of dependence of resistance on the dimensions of conductor. Initial portion where I will try to explain to you the another portion in which I try to divide the area into two parts. What will happen in this case scenario? So, let me stop it here only. In the next lecture, I will move in further discussions from this portion here. So, thank you.